Maillard telling us about a project in the same general kind of space, showing how we can do pleasant verification for a nice set of effects, and presenting a kind of algebraic framework for thinking about how to build different verification tools for different kinds of effects.
Thank you very much for the introduction. 1, 2, yeah, good. So this talk is kind of in the line of the previous talk, meaning that I will be talking about trying to move to have some effect on my slides. Yeah, seems better. So about effects. So when we are programming things, we are often starting as functional programmers with a pure base. And then when we want to interact with the external world, we are using all kinds of effects in the form of input-output, of manipulation of state, of non-determinism, well, all these little things that are around there. And if you want to think about these effects and to verify programs with respect to this effect, you need some kind of model to do that. So we represent effects in this talk as monads, and we are wondering about how to represent specifications. And what I will show in this talk is that we can also represent specifications as monads, and that in order to do verification, practical verification of program, we can use monad index monads that will give us a tool to have actual verification of code. So it's like monads all the way down. So what kind of tool have been used to verify effectful programs? So effect-specific program logics have been heavily explored in order to give specification and meanings to programs and to actually derive proof that a program satisfies some specification. In a more dependent type setting, whole type theory and Dijkstra monads provide a way to encapsulate a monad together with a specification in order to prove that a particular program meets its specification. One problem with this approach in our regard is that they are kind of specific to the effect. And we want to do it generically in the computational effect that we start with. And when we are considering a general monad, computational monad taken out of this set of effects, the questions that we need to face are what is the shape of specification and how do we actually verify programs if we have some notion of specification for programs in M. So let's go back to the beginnings. Hoare logic. With Hoare logic, we specify programs with a pair of a precondition and a postcondition. Usually programs are stateful programs that access to a state, and preconditions are then predicated on the initial state, postcondition are predicates on the final value and final state. Dijkstra got an extremely interesting idea with respect to these Hoare triples, meaning that if you want to prove a Hoare triple, you can actually reduce the problem to finding some weakest precondition that can be computed out of a program and which is kind of universal among the preconditions that the program can satisfy. And if we try to look at the type of this weakest precondition for various kind of effects that people have been looking at, we see that weakest precondition for pure computation are predicate transformers that maps postcondition and result value to precondition. In the stateful case, we'll have some piece of state lying around, meaning that we'll map postcondition on return value and final state to preconditions on initial state. And if we have exception, for example, we'll have postcondition on either return values or exceptional state, and we'll transform it into a precondition, which is just a proposition. Now, if we look at this type of predicate transformer, one thing that we can note is that it's actually the type of a monad. It's the type of a continuation monad to proposition. And the monadic operation on this continuation monad correspond to operation that we are actually doing on specification, meaning that the return is exactly the specification, like the most precise specification we could give to returning a value into a context. And the bind operation correspond to composing the specification that we would have for two computations. And we can play this trick actually with the other examples of stateful computations or computation with exception, and obtain, in this case, monads encapsulating specifications for this kind of computations. And actually, we can do that not only for predicate transformer mapping postcondition to precondition, but we also have monadic structure on forward predicate transformer mapping a precondition to the strongest postcondition, for example, that the computation should hold, or even for pre and post condition. And so all these kind of monad actually share some kind of interface, meaning that they are actually equipped with an ordering corresponding to how strong is one specification with respect to another. And the bind operation on these monads is monotonic with respect to this ordering. And so we can kind of, our goal is to use this kind of specification monads in order to specify programs with all kinds of effects. So how do we come up with specification monads for other effects? Well, one nice thing to notice here is that if you look at these three specification monads made of predicate transformers, they are actually following some kind of pattern. And the pattern is given actually by applying some kind of transformation to a basic specification monad, namely the continuation monad to proposition. And this transformation is actually something well known. It's just a monad transformer. So one nice insight is that if you have a basic specification monad and you want to enhance it to be able to talk about other kind of effects, you can do that. Like one way for doing that is actually to apply monad transformers to extend the specificational power of your specification monad. So now that we have something to talk about to encapsulate specification, and since it is a monad, it is on the same kind of footing as the computational monad in which our effects live. But we would like to know how to go from how to connect this computational monad and this specification monad. What we are using in this talk are effect observation, a function which explains how the computational monad should be interpreted in the specification monad. And so what is an effect observation? It's actually just a monad morphism, meaning a function assigning to each computation a specification and respecting the return and bind. So we can really see it as one way, like one choice of an interpretation of computations as specification. Let's look at some examples. For example, for non-determinism, we could, so we take finite subset of a type as the computational monad to encapsulate non-determinism, and we can give an observation to weakest precondition, like mapping a postconditional result value to a precondition, by saying that such a specification is valid for some set of potential results if it maps some postcondition to the precondition that asserts that all possible return valued holds of that postcondition. Another choice is actually to be kind of optimistic. That was the Gumbler effect observation of the previous talk. And it maps a postcondition to the precondition, which is, okay, there is at least some way to make the computation satisfy the postcondition. So this means that we have some, when we are describing an effect and a specification, and we also have some kind of choice in how we want to observe the effect in order to do verification. Not only can we choose a different kind of effect observation, we can also choose different kind of specification monads. For example, for input-output, when we are interacting with the world, we could have a first choice of specification monad that's collecting all the history of events since the beginning of the computation, and this history of events is used in the specifications. So that's a really rich kind of specification. However, sometimes it might be too rich, and it depends on the actual context of I/O events that occurred up to the point. So a more efficient, in some sense, representation of specification is to drop that context of history and only to consider the local I/O events done by a computation. So of course, we cannot specify all kind of interaction patterns with this smaller type of specification monad. But we can already do quite a lot of things, and these are actually much easier to use in a bigger program. So now that we have an example of specification monad and computational monad, we would like to do practical verification with them. And the way that we will be using here are Dijkstra monad. So what is a Dijkstra monad? It's a way to connect together the computational monad and the specification monad by indexing the computational monad with a specification, meaning that my type D of A at specification W will capture exactly the computations that satisfy the specification W. It comes with variants of the usual monadic operation, return and bind, which are indexed, and the index itself is using the monadic structure of the specification monad. So Dijkstra monads have been used a lot in the F-star proof assistant. They have been put in practice in quite large projects already that are actually already shipping code. And the very nice thing about these Dijkstra monads is that you can use this indexing to generate verification condition relying on the type inference. So you don't need an off-the-shelf system. It's just everything is coming from the type inference. So F-star is shipping a fixed set of computational monad. And there is also a system to try to define your own Dijkstra monads out of some schemata, which allows you to mix state and exceptions. But we actually want to be able to do that for all computational effects. So how do we do that? Well, starting from a computational monad, a specification monad, and a choice of effect observation between the two, there is one relatively simple way to describe a Dijkstra monad out of it. Namely, taking the Dijkstra monad at type A and specification W to be those computation in M of A, such that the specification assigned by the effect observation to this computation is stronger than the outer specification W. And using this construction, we can actually show that there is a categorical equivalence between, on one side, Dijkstra monads, and on the other side, effect observation. So let's put that in practice. If I take this effect observation for demonic non-determinism that I showed you earlier, I can use that, currently in F-star, to describe a new Dijkstra monads in which I can define choose and fail operation, which allow me to do non-deterministic computation with inference of verification condition at the same time. So you can see that in the choose operation, the specification is saying that I will answer at the same time true and false. And in order to use that in practice, you can, for example, generalize this choice operation to a pick operation that takes a list and non-deterministically takes an element out of this list. So to have a summary of the methodology, we start with a computational monad. Then we have some choice in the specification monad that we want to use. So we can choose more or less expressive one depending on what we want to achieve. We define an effect observation. We also have choose for that. And finally, we derive automatically from it Dijkstra monads. And we can actually use that in practice to do verification of effectful code. And this combines extremely well, but not with my slides, with monad transformers. So if you have any monad transformer, you can actually apply it to the identity and get some monad. And you automatically have one canonical effect observation and specification monad associated to it. And this actually subsumes the previous construction in F star of Dijkstra monads for free. So the P in ICFP is for programming. So can you actually use it? Yes, you can. There is so many new Dijkstra monads now in F star, and that we can implement and that we couldn't implement before. And we have a proof of concept in Coq, which is describing what is a Dijkstra monads and implementing quite a few of them. So this is in a really, really similar to what has been done for like the last 15 years in why not, in whole type theory, for a lot of kind of computational effects. And we hope that with this thing, we can actually try to have even more computational effects in this flavor. So also in the paper, we have examples of specification monads, of effect observation, of connection between specification monads, how you go from one to the other. There are often Galois connections connecting them. We have been investigating algebraic effects and handlers, in particular, whether it's possible to define handlers for Dijkstra monads. And it's sometimes possible. Let you see in the paper for the more complete answer. And we also have a mechanical derivation of monad transformer out of a meta language, which means that we can actually recover more closely what was done in Dijkstra monads for free. So for future work, we are currently trying to investigate larger case studies, which are not just one-liners. And we also have like some kind of continuation monad transformer, pseudo-transformer that we can derive. And I don't know, maybe we could do something with continuation. I hope the next speaker will tell us more about it. And we're also looking for effect observation for relational reasoning. And on this, thank you very much. I will be taking questions.
So let me start with a question from Slido, which seems to have somehow escaped the scope of another talk. Ironically, a troublemaker named Wouter asks, can you handle limited continuations?
So I'm pretty sure that I currently can't. I'm not even sure actually how to represent the limited continuation in as monads, to be honest. Maybe I could represent the syntax and try to do something out of it, but I wouldn't say that it would be extremely understandable yet. Yeah, I guess there is more work to be done to try to tackle that and to understand the limited continuation too.
Okay. In-person questions. We have plenty queued up here, in case not. Sounds like everyone's going virtual these days. Let's see, highest rated question. Why work on the Dijkstra monad rather than affect observations directly? Is it for compatibility with previous work, or is there a deeper reason?
Extremely good reason. So actually, we could indeed start to do verification just with effect observation. One problem we tackle when we try to do just effect observation, like just to use effect observation, is that typically you will apply the effect observation to your program and then start to prove something about the specification that you obtain out of it. And for example, if you have recursive call or if you have inductive hypothesis or something like that, you will get stuck at some point with your effect observation applied to some things. And at this point, you need to do some work with your hypothesis in your context to actually, well, match the two together. And Dijkstra monads kind of do that for you, meaning that they are inferring automatically the specification of the body of a function, for example, and then you are left with a verification condition only at to show that the type that you prescribe for the specification that you give to the function match the specification inferred for the body. So it's kind of, it helps to have some kind of modularity.
Let's see, someone right behind you beat you to it by 1 second.
Can you also handle non-terminating programs? I mean, I know it's not very useful to describe the state, but there might be useful and meaningful I/O effects for non-terminating programs.
Yeah, indeed. Like, no, non-terminating program is indeed extremely interesting, like to be able to specify what happens. And as long as you have a good model of non-termination as a monad, so for example, we have been trying using McBride's encoding of non-terminating program by just a free monad, and yeah, you can actually do things with that. It's some work, but it's possible.
So maybe Andre can ask his question in person now.
Okay. I hope I still remember it. I wonder where these specification monads come from. Like, of course, if you're like very smart, you just come up with one. But suppose you have like an algebraic theory of effects, like given by some operations and equations, like non-determinism. Then there will be two natural choices: the angelic and demonic, the N and the or, and so on. Is there some method to this madness? Like, is there some methodology by which you think you could get the specification monad corresponding to some given effect?
So I don't know if a specification monad itself can be like described for some effects, but once you choose some specification monad, for example, the continuation monad to proc, you have kind of canonical ways to provide effect observation. Like, for example, this angelic and demonic effect observation correspond to algebra structure that you can impose on your algebraic theory. And so there are principal ways to come up with the effect observation themselves, but it depends on the specification monad. If, for example, I were to take a specification monad, something that were returning like resources, for example, natural numbers, then I would have another kind of algebra that I could try to describe. But yeah, so there is quite a lot of choice, and the fact that we are free to choose this kind of stuff also helps when we want to verify programs.
Okay, let's thank Kenji.